The calorie lie. Why food math doesn't explain weight gain. What if everything you've been told about calories and weight loss is only half the story? You've probably heard it 1,000 times, just eat less and move more. But if weight gain were really that simple, why do so many people struggle despite counting every calorie and following the rules perfectly? What if the problem isn't your willpower, but the way we've been taught to understand food and fat loss in the first place? For decades, public health messaging has emphasized a straightforward equation: calories in versus calories out. According to this model, if you consume more calories than you burn, you gain weight. If you burn more than you consume, you lose weight. While this framework is grounded in the basic physics of energy balance, many researchers and clinicians argue that it is an oversimplification of how the human body actually regulates weight. The phrase calorie lie does not usually suggest that calories are meaningless, but rather that relying on food math alone fails to capture the biological, hormonal, metabolic, and behavioral complexities that influence weight gain. A calorie, in scientific terms, is a unit of energy. In nutrition, we typically use kilocalories, which measure the amount of energy food can theoretically provide when metabolized. On food labels, calorie values are calculated using standardized formulas based on average energy yields: approximately 4 calories per gram of carbohydrate, 4 per gram of protein, and 9 per gram of fat. These numbers are derived from laboratory measurements using combustion techniques, where food is burned in a device called a bomb calorimeter to determine its total energy content. However, the energy released by burning food in a lab is not identical to the energy your body extracts during digestion. The human digestive system is not a furnace, and it does not absorb all nutrients with perfect efficiency. This discrepancy is one of the first cracks in the simplistic calorie counting model. Research has shown that the actual energy absorbed from certain foods can differ from what labels indicate. For example, whole nuts such as almonds and walnuts contain fats that are partly trapped within fibrous cell walls, meaning that a portion of their calories passes through the digestive tract unabsorbed. Cooking methods also affect how much energy the body can access. Cooked starches are generally more digestible than raw ones, increasing their bioavailable energy. Individual differences in gut microbiota further complicate matters, as different bacterial compositions can extract varying amounts of energy from the same foods. In short, calorie numbers are estimates, not precise reflections of what each person's body will absorb. Even if calorie labels were perfectly accurate, the body's response to calorie restriction or excess is not mechanically predictable. The traditional calories in, calories out model implies that energy expenditure remains relatively stable and that reducing intake will reliably produce weight loss. In reality, the body adapts. When calorie intake drops significantly, metabolic rate often decreases as well. This phenomenon, sometimes called adaptive thermogenesis, reflects the body's effort to conserve energy in what it perceives as a period of scarcity. Resting energy expenditure can decline, spontaneous physical activity may decrease unconsciously, and hormonal shifts can increase hunger. These changes make sustained weight loss more difficult than simple subtraction would suggest. Hormones play a central role in this process. Insulin, for example, regulates blood sugar and promotes fat storage when elevated. Diets high in refined carbohydrates can cause repeated spikes in insulin, which over time may contribute to insulin resistance and altered fat metabolism. Leptin, produced by fat cells, signals to the brain that the body has enough stored energy. When body fat decreases, leptin levels drop, often increasing hunger and reducing metabolic rate. Ghrelin, known as the hunger hormone, tends to rise during dieting, stimulating appetite. Cortisol, released during stress, can influence fat distribution and cravings for high-calorie foods. These hormonal dynamics show that the body actively regulates energy balance rather than passively obeying a mathematical equation. Another challenge to the calorie-centric view is the concept of weight set point theory. According to this hypothesis, the body defends a certain weight range through coordinated hormonal and metabolic mechanisms. When weight falls below this range due to calorie restriction, the body may respond by increasing hunger and decreasing energy expenditure, pushing weight back upward. Conversely, when weight increases above the defended range, appetite may decrease, and energy expenditure may rise slightly. Although the exact mechanisms and degree of set point regulation are still debated, many researchers agree that body weight is not infinitely flexible in response to calorie manipulation alone. This helps explain why many individuals who lose weight through strict dieting eventually regain it despite continued efforts to control intake. The quality of calories consumed is another critical factor often overlooked by simple food math. The body processes different macronutrients in distinct ways. Protein has a higher thermic effect of food, meaning the body uses more energy to digest and metabolize it compared to fats or carbohydrates. Protein also promotes satiety more effectively, reducing overall calorie intake naturally. Fiber-rich carbohydrates slow digestion, moderate blood sugar spikes, and support gut health. In contrast, highly processed foods engineered for palatability may encourage overeating by combining sugar, fat, and salt in ways that override normal satiety cues. Two meals with identical calorie counts can have dramatically different effects on hunger, hormones, and subsequent food intake. Ultra-processed foods are particularly relevant in discussions of the calorie lie. These foods are often energy-dense, low in fiber, and rapidly digestible. They can produce quick rises in blood glucose and insulin, followed by drops that trigger renewed hunger. The body responds not just to how much energy is present, but to how that energy is packaged and delivered. Lifestyle factors further complicate the equation. Sleep deprivation has been shown to alter levels of ghrelin and leptin, increasing appetite and preference for high-calorie foods. Chronic stress can elevate cortisol, which may contribute to abdominal fat accumulation and emotional eating. Sedentary behavior reduces total daily energy expenditure, but it may also affect metabolic health independent of calorie burn. Physical activity, beyond burning calories, improves insulin sensitivity, supports muscle mass, and influences appetite regulation. These interactions demonstrate that weight gain is not simply a consequence of miscalculated arithmetic, but of a complex interplay between biology and environment. The body is a dynamic system with feedback loops, not a static ledger. Calorie counting can still have practical value. For some individuals, tracking intake increases awareness of portion sizes and eating patterns. If you enjoyed this video and want more eye-opening insights on nutrition, health, and the science behind weight loss, make sure to hit that subscribe button and turn on notifications so you never miss an update, because understanding your body is the first step toward transforming it.